Okay, so let's look at how we can describe this wave and a string. So as I showed to you guys earlier, if we have this, string, especially if we had, tighten this side here and then probably applied, or apply the tension from both sides here. You see, maybe you can see here better, right? Wave, right? Okay, so let's say this string we have here, instead of like this, I'm going to exaggerate and make it something like this. Let's assume this string, it's gonna be like something like this, because originally it was like this, but once it's in, vibration, it's like this, okay? When we block it up, it's gonna be like this. And then that is due to the tension. When we pluck this spring up here, what happens? There will be tension here on this side here, right? So tension T, this in this segment. There will also be tension T on here. Let's consider maybe, let's say this is called, let's call P and then Q end of the string, okay? So maybe this much of the string, PQ. Now, string, important thing about the string is that string is flexible, it's long, its length is longer in comparison to its diameter, okay? So that's how we define this string. So now we want to maybe take some particle here, okay, some particle here at the point where we're blocking here. That's the particle in this string, okay? So this, we have a tension on this side, we have a tension here. Assume, so originally it was like this, right? So what I'm gonna do is I'm gonna just draw this here, just to make a coordinate system here. Let's call point O. Now let us resolve this tension into two components, okay? Because we have a T, right? So so if we resolve this, maybe what we could do is actually we could also take a smaller portion here. Let's take a small segment of this, okay? So let's not the whole PQ. Let's take A and then the B small segment, A, from A to B segment, okay? That much of length here. So now in this we have a tension this way, right? So we want to resolve this tension into rectangular component, meaning two different parallel and perpendicular component. When do we resolve that? Oh, I forgot to, yeah, so let's make another line here also. This is just for our purpose of calculation. So I'm going to just make this only for purpose of calculation here, okay? Just coordinate system really. So let's say this angle is some theta by 2, okay? You could choose really theta, it doesn't matter whether you choose theta by 2 or theta really. It will work out at the end. So I'm just choosing it because when I do theta by 2, it's easier to do calculation later on, that's all. So there is a tension along this line, right? Like here, tension along this way. So that T has to be resolved. So this side becomes what? T cos theta by 2. And then this side we will have what? T sine theta by 2. Okay? Now, next thing we want to do is I want to just drop from here all the way to here, okay? So maybe maybe that should not be O, it's probably over here. Yeah, if I drop point here, so I'm gonna just change this as O here, okay? So this is O. I'm just doing this here to show you something after some time, okay? So this is the point O, so I'm just dropping it down here. And then if you use a geometry, it turns out that this angle becomes theta by 2. Now what we are going to do is same thing here. This portion here, we have a tension along this segment here, this part here, if we resolve it, we get what? And assume this angle is also theta by 2, okay? Then tension, again, when we resolve, this part becomes t cos theta by 2, okay? So this is going that way, and then we will have another part of, you know, this t, that will be t sine theta, so that will come here, so we'll have another t sine theta by 2 plus again t sine theta by 2. So if you notice here, this t cos theta, they are in opposite direction, so they get, you know, these two guys gets cancelled out. We don't need to worry about that. So, but then we have this tension t sine theta by 2, really 2 times of t sine theta by 2, and this tension seems to be responsible for the centripetal, you know, motion of this part here, okay, for this particle here. So, I mean, for this string, sorry, not particle, please. So let's assume this string of a segment, let's call it segment AB, has mass m, okay? And then assume the wave is traveling to, let us call to the right, this with speed v, okay, in the string, right? And now, if we look at this, oh, and I forgot to do this part here. So I can also drop this, you know, part of this here, just do some mathematical construction, okay? This becomes theta by 2 here. So idea is this angle and this angle should give you the, you know, this same angle here. So what we'll do here is this theta by 2, and we'll talk about that in a minute. So since this tension total t sine theta by 2 plus t sine theta by 2, this net force is, you know, is responsible for providing centripetal force, which means this must be equal to what? mb squared by r. What is r here? You may say r is really this r. R is the, it's kind of getting too crowded here, so I'm going to write r as here, okay? So same thing, either this distance or this really r, this distance, or this, if we assume it is small, okay? So r is the radius of curvature there. Now, this one, if we add there, this is just 2t sine theta by 2 equal to mb squared by r, okay? So let's, so for, you guys may not be able to see it, I'm going to write down up here. So erase this part. So for very small angle, for a small angle theta, sine theta, we have a sine theta by 2, right? Sine theta by 2 or sine theta is really equal to theta, okay? Does this make sense? Maybe not. So think about this. Sine has a maximum value when sine is 90, right? So 90 means it's 1. Let's bring it down. Sine 60 is what? Root 3 by 2. Okay, that's smaller than 1, right? And then sine 30, which is 0.5. So as we are decreasing the angle, the value is getting smaller. When this angle, this part, this argument here is very, very small, so a small angle theta, or you could also call just theta by 2 here, just to be specific for this case, sine theta by 2 must be, you know, this sine theta by 2 must be equal to theta here, okay? So this is the, wait a minute. not theta by 2. Sine theta, I'm sorry guys, forgive me for that. I'm gonna erase this and write this down here. So for small angle theta, sine, not theta by 2, sine, let's write it. Sine theta is equal to, close to theta. This is called approximation, okay, so just approximation. So I told you a reason, right? So sine 90 degree is 1, sine 30 degree is 0.5, sine 1 degree is, I don't know what is it, but it gets really small. So when this part is really small, it becomes close to the value of that angle. Okay, that's what we are saying here. So sine theta is close to theta. So here, instead of sine theta by 2, we should be able to just write theta by 2 there. Okay, that's what I was trying to do. Okay, so this means from this equation we could write 2t. Instead of sine theta by 2, we should be able to just write theta by 2, and that must be equal to mb squared by r. Okay, so I want you guys to label this as some equation. Let's call this as equation 1, just giving it a name. Now, and then you can actually cancel this out. And then, okay, let's do this. T theta equal to mb squared by r. This is neat than this one, so let's write that as equation 1. Now, let's say, this is very specific to this part of a string, right? That is also only for segment A to, from here to B, where it looks more like, so almost like a circle, right? Like curvature. Well, why is that helpful? It's not really helpful, right? I mean, we don't know which string it is talking about. Or let's say we decide to, use this whole string. Then if I want to do some sort of experiment, I have to keep measuring the mass of this string for different length. Well, that's kind of tedious. We don't want to do that. So, to avoid that, what we can do is we can define a quantity called linear mass density. Okay, so let's define a quantity called linear mass density. Mu, label as mu, okay, Greek word here, mu. Linear mass density is mass per unit length. Okay, so what does that mean is mass per unit length. If we take about a meter of a length here, mass of this meter, mass of this length divided by this 1 meter will give me some value. That quantity is a mu, okay? Now, instead of that whole length, we want to do only half of the length. When we change the length from, whole, like full 1 meter to half meter, what happens? Mass will also change, right? And then the length also changes. So this ratio, linear mass density mu is it's a constant, and it constant for the given material. Okay, so linear mass density is a mass per unit length. Now let's say let the length of segment, we talk about the segment A to B, AB equal to some delta x, okay? Just giving it some small length, that's what I'm saying when I said delta x means, okay? Small length, alright? Okay, then we know now the linear mass density, we have the length delta x. In this equation, we don't want to use mass m because m depends upon different, string, right? Like different part of the same string, m depends upon that. So we want to remove that, and we want to replace it by some sort of, some parameters that can have a constant influence there. Okay, so in place of m, we should be able to do something here. So we should be. I'm going to write it on the top. I don't know if you guys see it here at the bottom. So mass m can be written as what? Linear mass density mu times delta x unit length. Okay, you see this, because this is a ratio of what mu is. I'm going to write this down here. So mu is something like this. Mu in general goes like this: mass, let us say m by L. Okay, mass per unit length. Here in our case, mass is just m, our length is tiny delta x, that's why we have this. So, you know, then mass m equal to just mu times L, and our mu is mu, our L is delta x, okay? So just a small length. So this length is our delta x, okay? Alright, so we are going to replace with this, you know, m with this quantity in this equation 1. So let's do that and see what we get. So if we do that, we will end up getting t theta equal to mu delta x v squared by r, right? Okay, all right. Now, important thing here, it's minor, but I don't know, maybe it's possible you guys forgot about this. Do you guys remember what's the relationship between, you know, if you have some small angle, some theta, and then you have an arc length, some L, and then it has some R radius R here. How are these quantities related? L is the arc length, R is the radius of the curvature, theta is the angle subtended by this L. Theta is given as the ratio of the arc length L divided by the radius of curvature R, okay? So in this case, our theta is what? This whole thing, theta by 2, if we add that becomes the total theta here, and that theta is subtending an arc, which our arc is AB, which has the length delta x, and then R is the radii here, radius of this curvature here, okay? So we should be able to write here, in place of our theta, we should be able to write theta equal to what? Delta x by R, which is equal to mv squared by R. Oops, sorry guys, not m. This is mu. Please go back and change in your note. I'm sorry, I missed this. Forgive me. Mu, okay? We cannot, mu and m are not same. So we cannot exchange those two. Alright, so this guy R and R gets cancelled, and then which means I am also missing delta x here. Okay, so mu delta x, so this delta x and delta x gets cancelled, okay? So, guys, I forgot to carry this down here. So mu delta, you know what? I'm going to rewrite this, so in case you guys got confused just like me, and then so let's make it nicely here. So in place of theta, theta is what? Delta x over R, which is equal to now what? Mu delta x b is squared by R, okay? That's what I was trying to write. So now delta x and delta x gets cancelled, R and R gets cancelled, so we are left with t by mu equal to b squared. And then if we rearrange this, we get v equal to square root of t by mu. Alright guys, so I have been writing t here. Okay, so this is the speed of the wave on a string, okay? Okay, so now, very, very important, this t is not a period, this is a tension t. Mu is a linear mass density of the string, you guys already know that. So let's make a distinction. I have been using t here, so what I'm going to do here is, finally, just to tell, you know, my mind and even your mind that t is tension, let's replace t by t subscript s, means tension on the string, okay? So we don't get confused between the period t and the tension t, okay? This is very, very important. So I'm going to write this equation here. So therefore b is equal to square root of t subscript s. tension on the string divided by linear mass density mu. Okay? Alright guys, so very important. So the speed of a wave on the string is given by what is square root of ratio of the tension on the string to the linear mass density of the string. Okay? So this TS, very important, this is not a period, this is the tension on the string. Please burn this into your head so you don't make, you don't get confused and then do the wrong calculation. Alright? So take a moment to just quickly go through this. And of course I will not ask you anything with the derivation in the exam or anything, but I thought it is important for you to kind of see a little bit, it's not a lot of math here, a little bit of where this equation come from. Okay? Okay, so